Hello and welcome to the Unit 10 Section 2 video on interpreting data. So in the last section we talked about how do you create a box plot, how do you create a histogram, how do you create a dot plot. Now we're going to talk about how do you interpret that data. So histograms graphically show how frequently every value of a data set occurs, making it easy to determine the most common and least common values. In a histogram, the type of data being measured is represented on the horizontal axis, and the vertical axis represents how many observations are in each data type. So, knowing that, let's take a look at an example. A car salesman records the number of cars he sold each week for the past year. The following frequency histogram shows the results. So, what is the most frequent number of cars sold in a week? Well, we just look for the highest bar on here, and that is 4 cars sold. For how many weeks were 2 cars sold? Well, we go over here, and we see that it happened 9 weeks out of the year. Determine the percentage of time 2 cars were sold. So we take the 9 weeks that we sold 2 cars, and we divide it by the number of weeks in a year, which is 52. And if you were to add up all these frequencies, they would add up to 52. And then you would get the approximate answer, which would be 0.17. So that would be about 17% of the weeks out of the year we sold 2 cars. Now let's talk about interpreting box plots. And you should have a pretty good idea on how to interpret box plots, considering we talked a little bit about how they are constructed. So box plots are useful for comparing many data sets at once. Box plots show the center and spread of a data set using the 5 summary values, the minimum, first quartile, median, third quartile, and maximum. And we discussed all of that. So this should be review from what we did in the last section. So let's take a look at an example reading box plots. So the box and whisker plots show the ticket sales in millions of dollars of the top 25 movies in 2000 and in 2007 for the United States. So which data set has the greater median? And we want to explain. So I'll go ahead and type this out just so you can read it a little bit better. So, because we do have to do some explaining. So the data set for 2007 has a greater median since the vertical line in the box for 2007 is farther to the right than the vertical line for the box for 2000. So let's explain this. 2007 has the greater median because here's the median right here in the middle, and it's farther to the right than the median here. So therefore, since the vertical line for 2007 is farther to the right than that of 2000, 2007 has the greater median. Which data set has the greater interquartile range? Well, that again would be 2007. The data set for 2007 has a greater interquartile range since the length of the box for 2007 is greater than the length of the box for 2000. And then the final question is about how much more were the ticket sales for the top movie in 2007 than the top movie in 2000. Well, here we're looking for our maximum values, okay? So the maximum value in 2007 is about 335 million, and the maximum for 2000 is about 260 million. Because remember, these values are in millions, okay? So The greatest value here is about 260. The greatest value here is about 335. Okay? And then all you're going to do is take those two values and subtract them. 335 minus 260, 260 is equal to 75. So we're going to finish this off by saying the ticket sales for the top movie in 2007 were about $75 million more than for the top movie in 2000. All right, now let's talk about interpreting dot plots and the types of distributions that you can have. A dot plot gives a visual representation of the distribution or shape of the data. So a uniform distribution, all the data points have nearly equal frequency. It doesn't have to be perfect, but this is a fairly uniform distribution. In a symmetric distribution, the vertical line can be drawn, and the result is a graph divided into two parts that are approximate mirror images. So this side of the graph looks about the same as this side of the graph. In a skewed distribution, the data is not uniform or symmetric. It may be skewed to the right, which is what's shown here, or skewed to the left. The side that has more data is the direction in which the data is skewed. So in example 3, the dot plot shows the number of miles run by members of 2 track teams during one day. We're going to explain what the data distribution means. So for team A here, the data for team A show a symmetric distribution. The distances run are evenly distributed about the mean. For team B here, the data for team B show a skewed right distribution. Most team members ran a distance greater than the mean. So that's how you make those interpretations. More people here were running faster than the average. Here, they were evenly distributed. Now, the data is great when everything is nice and evenly distributed and everything like that. But what happens if you have an outlier? What if you have one piece of data that completely screws up the data set? Sometimes you have to make those identifications. That's what we call an outlier. A value that is very different from the other values of the data set is an outlier. In the data set below, one value is much greater than the other. So most of your data is sitting here, but then we have one value that's way up here, and that pushes our mean here, which puts our mean higher than most of our data. So in this example, example 4, we are going to identify the outlier in the data and determine how the outlier affects the mean, median, mode, and range of the data. So first thing we're going to do is we're going to arrange this data in numerical order. Okay, that's always a good place to start. So we've got 5, 7, 8, 9, 10, 12, and 54. And when you do that, you can very easily see which one is the outlier. So here, the outlier is 54. So with the outlier, let's determine these pieces of information. So the mean is going to be, with the outlier, 5 plus 7 plus 8 plus 9 plus 10 plus 12 plus 54 divided by the number of pieces of data we have, which is 1, 2, 3, 4, 5, 6, 7. And that's going to give us 15. So our mean is 15. The median here, since we have 7 pieces of data, we just pick the middle one. The median is 9. The mode, well, since every value only occurs once, there is no mode. And the range, if we do 54 minus 5, our data range is 49. Now without the outlier, we're going to do our same mean, but we're going to leave out the 54. We're going to leave out our outlier. So here we have 6 pieces of data, and our mean is now 8.5. The median is also 8.5 because now we divide our data here. We've got 8 and 9, so halfway between 8 and 9 is 8.5. Again, we have no mode because we don't have anything repeated. And the range is now going to be 12 minus 5, which is going to be 7. So, in summary, what we can say is the outlier increases the mean by 6.5, the median by 0.5, and the range by 42. So it has no effect on the mode. So as you can see here, the outlier can strongly affect the mean of a data set while having little or no impact on the median and mode. Therefore, the mean may not be the best measure to describe a data set that contains an outlier. In such cases, the median or mode may better describe the center of the data set. So this is why we don't use the average or the mean for everything. Sometimes there are more appropriate measures in statistics to figure out where the middle of your data is. Let's finish off this section with misleading graphs and statistics, because it is important to know that graphs can be used to influence what people believe. The way a data set is displayed can influence how the data is interpreted. So it's a good practice to be able to recognize these things and see where the data may be misleading. So in example 5, this graph shows the size of tomatoes on plants that were treated with different fertilizers. So we're going to explain why this graph is misleading. Well, if you notice, the scale starts at 80 and goes to 86. So is there really that much difference between these 4 values? And the answer is no. The scale on the vertical axis begins at 80. This exaggerates the differences between the sizes of the bars. So what may some people believe because of this graph? Someone might believe that the tomato plant or the tomato treated with fertilizer D is much larger than the other tomatoes. It is only 3.3 grams larger than the tomato treated with fertilizer B. Okay? So while in the graph it may look like a big difference, in reality the difference is not as big as you would be led to believe just looking at this graph. And a lot of it is because we start at 80 and go to 86. This is a fairly short range, and it makes the differences look much larger. In example 6, the graph shows an average price of gasoline in the US in September. So why is this graph misleading? Well, the intervals on the vertical axis are not equal. So if you notice, we go from $1 to $1.10 to $1.12 to $1.14, $16, $18, $20, and then we jump up to $1.40 and $1.60. So because our axis is uneven, it makes this jump look much bigger than it really is. So what might people be led to believe just looking at this graph? Well, someone might believe that the price of gasoline increased the most between let me get this here, between 1995 and 1997, because on the graph, that looks like the biggest increase between 95 and 97. However, the change between 1995 and 1997 was only 14 cents a gallon, while the change between 1999 and 2001, which looks much smaller on this graph, was 17 cents a gallon. So the change between 95 and 97 is actually smaller than the change between 99 and 2001, and it all comes from the fact that this scale is not even. All right, example 7. The graph of what percent of the total votes were received by 3 candidates for student council president. Okay, so we are shown how many votes these candidates received. Why is this graph misleading? Because the sections of the graph do not add to 100%. Okay, we have 20, 10, and 5, so it only adds up to 35%. So the votes for at least one of the candidates are not represented. So what might people be influenced to believe by this graph? Someone might believe that Smith won the election. Now, that could have been the case, but we don't necessarily know that for sure because we don't have all of the information. So when you have a pie chart like this, you need to have 100%. You cannot have less than 100% as parts of the pie. Now, statistics can be misleading because of the way data is collected or the way results are reported. A sufficiently large random sample is a good way to collect unbiased data. In a random sample, all members of the group being surveyed have an equal chance of being selected. So, for example 8, a researcher surveys people leaving a basketball game about what they like to watch on TV. We want to explain why the following statement is misleading. The researchers found 80% of people like to watch sports on TV. Well, why is this misleading? Well, the sample that was collected is biased because people who attend sporting events are more likely to watch sports on TV than people who watch TV but do not attend sporting events. Okay, so this is all about interpreting data and knowing what you're looking at and knowing where issues may lie. Okay, so it's always good to be mindful of the issues with the data that you're being presented and how to improve upon those issues. Okay, so that concludes this section, and it also includes the short unit on statistics. Again, this was more so a introduction to statistics and a little bit of a preview on the things to come. So, in a probability and statistics course. And with that, that concludes the entire course of geometry.